Good evening, everybody. Good evening, Professor Martin. Good evening, Mr. Dr. Ibrahim Tijani. Good evening, everybody in the room here. Good evening, Mohammed, Dr. Mohammed Fellah. We start.
I'm ready for me.
تفضل. Again, good evening, everybody. I'm starting Arabic Skillet. Another that Dr. Ibrahim Tijani, he make it the CV of Professor Martin. السلام عليكم جميعا ورحمة الله وبركاته. اليوم نفتتح البرنامج الجديد على أكتاف العمالقة الذي نستضيف به نخبة من العلماء الذين نفتخر بهم، وأيضا كوكبة من العلماء الذين موجودون معنا داخل الغرفة وخارج الغرفة. Professor Martin Rees welcome to the first guest in همسة سماء الثقافة here in Denmark. Today we start with Dr. Ibrahim Al-Tijani to say the CV of the kids here. Dr. Ibrahim Tijani, the mic with you. Dr. Ibrahim, mic open.
السلام عليكم ورحمة الله تعالى وبركاته. مساء الخير، ونقول اللهم صل وسلم وبارك على سيدنا محمد الفاتح الخاتم وعلى آله وصحبه وسلم تسليما كثيرا طيبا مباركا فيه. حقيقة في المبتدأ نحيي الحضور جميعا كل باسمه ورسمه وشخصه. اسمحوا لي أن أتطفل في مائدة العلماء وأن أحاول تقديم غامة علمية على المستوى العالمي، وهذا الرجل القامة والذي شارف على 90 من عمره ولا زال عطاؤه حول العالم، هذا العطاء الثر، العطاء المتميز في مناحي الحياة المختلفة وما يعود عليها بالخير والنفع على البشرية في مشارق الأرض ومغاربها. أسمحوا لي أن في عجالة أن أقدم ضيفنا لهذه الأمسية عبر منصة همس السماء الثقافة، ونحن نستضيف أول النبغاء وأول العلماء المتميزين الحاصلين على جائزة نوبل. ويسرنا في منظمة همس السماء الثقافة أن نرحب بالجميع. وفي المبتدأ والمستهل ضيفنا العزيز هو البروفيسور مارتن. اسمحوا لي أن أمر سريعا على سيرته العطرة وسيرته المتميزة وأقول مبتدأ welcome and good evening Sir Martin Press. More welcome, and we are happy to have you here, and really we are so glad that we are part of our this association with all this group and start in their field, in academical or in media or in any sectors or any field. So more welcome. Please allow me to just go through your biography and what you did since the first century, up to this moment, and the real add value what you did in the world, and regarding the scientific, regarding the helping the human being all over the world. So please allow me, sir, to just go through your biography in a quick, within 1 or 2 minutes. Sir Martin John Rees, he's born in June 1942 in York, in England. And he is an English cosmonaut, and he is astrophysicist who was a main expertise of Big Bang, theory, and origin of the universe. He had PhD degree in mathematics in 1963, master degree, and his doctorate, it will be in astronomy also in 1976 and Trinity College of Cambridge. And he was the president of the Royal Society between 2005 to 2010. And he's also member of institutions of advanced studies in Proctor in USA. And Sir Martin, he received a lot of awards during his lovely journey. He received many international awards, among them, for an example, he received gold medal of the Royal Astronomical Society in 1987, Albert Einstein Award in 2003, Isaac Newton Medal in 2012, and Derek Medical in 2013, and Ferris Zwicky Prize in 2020. He had many successful in his lovely journey. And actually, we are so glad and we are so happy that we have him as our first guest. So Mr. Mohammed, Dr. Mohammed Akram, and Dr. Fatima, and Mr. Rashid Khairi, allow me to say more welcome to Professor and Sir Martin. You are here with us, and we are looking to hear a lot of your experience during your lovely journey. So welcome again, and welcome Mr. Mohammed and Dr. Rashid. Thank you for all this and all our guests. So we are so happy. Let us to enjoy our evening with Dr. Martin.
Yes, thank you, Dr. Ibrahim Atijani. I have the Zoom have a problem in the live now. I'm waiting to fix it. The Zoom, the problem. It's not with us the problem.
I think we need to start, Dr. Fatima, with the interview. Then maybe you can fix it. Yes.
Yes.
So thank you so much for Dr. Fatima, for Professor Ibrahim Tijani, for also the organizers. I especially thanks Professor Martin Rees. It was my second time to meet him. As I said, I met him before in ICTP Summer School in Cosmology in 2014. I mean, it was a great pleasure for me to meet him at that time, and he was ICTP invited him to give him the Dirac Medal for 2013 with Cables and with James Peebles, which I invited him in the previous episode of this series. James Peebles is one of the biggest also cosmologists in our actual time. So, Professor Martin Rees, I mean, it is a great honor for me to have you with me in this series. The series, I initiated this series since the beginning of this year. I mean, to construct a bridge between the Greek names in theoretical physics and maybe Nobel Prize laureate in physics, and the Arab audience, experts or graduate students, researcher, or the normal audience. I invited many names, as I said, cosmologists, string theorists, quantum gravity experts, and I am very happy to have you. Maybe we started this interview to tell the Arab audience maybe a few words, and I am happy. I mean, so you can start to tell a few words to the Arab audience before starting our interview. Thank you.
Yes. Well, thank you very much. Can I just say how very much I appreciate being invited to speak to this group from many nations. I hope very much that international contacts will continue Of course, we all know that science is the most international of human activities, which can span all barriers of faith and nationality. That's why science is very important as a human activity. But of course, it is especially important because of the applications of science, which are crucial to us all. That's why physics is a central subject, and all its applications are as well. And I should just say, in response to what's been said kindly about me, that I'm an astronomer, but in my last 10 or 20 years, because I've been involved in science politics, I have broadened my perspective to think a lot about climate science and other threats which affect us all. So I have a broader perspective about how science is important and how we've got to make sure that science is used to maximize its benefits and to minimize the risks, because as we get more empowered by science, it can do more good, but also if it's misused, it can do more harm. So the stakes are very high, and it's up to us to ensure that we can keep the benefits of science and avoid disaster.
Yes. By the way, just to say about climates and other things I saw, I mean, before the meeting, your TED talk about, I mean, the end of the century. You said that you wrote a book and the publisher changed suddenly the title from end of the century to the end of ours. So yes. I don't know. Yes. Yes. So I think he didn't like the title. I don't know why, but it was really a good book. And most of the people who knows Martin Rees as cosmologist, astrophysicist, but they didn't know maybe this other achievements in climates and other things.
And can I just mention that I have a newer book called On the Future, which is translated into 20 languages, including Arabic.
It's a great honor for me. Yeah. Maybe we can send me maybe the PDF version, or I can search it for it and share it with the audience. Thank you, Professor, for this information. So maybe we can start right now with the interview. As I said to the audience, our organizing protocol is very well known. Like the previous series is half an hour to 45 minutes interviews, me and Professor Martin Rees about maybe cosmology, astrophysics. We start with the questions gradually by starting with the simple questions, then maybe we go to difficulty, then we open the floor to the graduate students and the researcher for 30 minutes for, I mean, discussing with professor or asking questions. So maybe we start right now with the interview. I think when we discuss about theoretical physics or physics in general, Professor, I think we need to discuss, I think you were students at Trinity College, Cambridge, and when you, I mean, when we hear Trinity College, I think the first name is Newton, Isaac Newton. And Isaac Newton was, I mean, the first maybe intellectual who think about the unification or achieve the unification between the interactions or the force which make the apple fall and the forces which make the orbits hold in their orbits. So the planets holds in their orbits. So after that, and he realized he put his theory of gravity, and it was working perfectly for centuries, and it was very precise for maybe many systems. After that, I mean, this theory of gravity faced many problems, and those problems, as you know, Isaac Newton, he didn't, I mean, clarify or explain why his law of gravity is inverse law, square inverse law, and how this gravity works. And other things, I mean, as most of the professor here and grad students know, and Einstein, I mean, after his achievement in 1905 in special relativity, and also making the principle of simultaneity, which knows that the principle of simultaneity is not working with this regime or this picture of gravity. So he gave us this new picture or new looking of gravity, which is Einstein's general theory of relativity. So my first question is, so how can you explain to the normal audience, as I said, we start by simple questions, how to discuss with, to explain to the normal audience the revolution of the general Einstein theory of general relativity, and what's the problems, the actual problems, or the limitation of this theory, like the Newton's one. So,
yes.
Okay.
Well, I think good you started with Newton. He was the best student we ever had in Trinity College. We are waiting for another one who will do as much.
Maybe, yes.
One anecdote about Newton. He had his idea about the apple falling being the same as the force that holds the moon in its orbit in the year when the universe was closed because of a plague. And he went back to his home on a farm in the north of England, and that's where he had his great thoughts. Well, as you can probably guess, the university has been closed for another plague all last year, and the students are coming back, and I'm wondering whether any of them will have had some great idea while they were away, just like Newton did. I doubt it, but it would be great if they did. So Newton did have that great unification, and I think it's important to say that Einstein didn't overthrow Newton. He sort of transcended and generalized Newton, because Einstein gave better reasons why all objects fall at the same speed, whatever they're made of, which wasn't obvious to Newton why that should be so. And also, Einstein's theory can cope with extreme situations when gravity is so strong that even light is affected by it. So Einstein's theory is a deeper understanding into the nature of space and time and how they're linked together. And of course, it does give slightly different predictions from Newton's theory, even in contexts where gravity is normal. In particular, the GPS system, which uses the satellite navigation, would be inaccurate if allowance was not made for the results of Einstein's theory that gravity affects the rate at which clocks tick. So Einstein's theory is important for these precise technologies. But of course, if we turn to cosmology and astronomy, we observe objects which are very extreme and where Newton's theory is certainly not good enough. We have known since the 1960s that there are some stars called neutron stars, which are so dense that they have about the mass of the sun concentrated in something just about 10 kilometers in radius. And the gravity there is very important. It would take a rocket going at half the speed of light to escape, and light's very severely bent there. And we then discovered black holes. These are objects which are so dense that gravity has caused them to collapse and cut them off from the rest of the universe, as it were, leaving a gravitational imprint in the space they've left. So by looking at the universe, we can find places where Newton's theory would be quite inadequate and where Einstein's theory applies, and indeed has been confirmed. There are tests of Einstein's theory which indicated it's very accurate to understand black holes and neutron stars. But you asked me to say, what's the next step? What about overthrowing Einstein, as it were? And the situation here is that we have two important theories that emerged in the 20th century. One is Einstein's theory of space and time, and the other, of course, is the quantum theory, which is the basis of our understanding of atoms and molecules and the micro world. And what we don't yet have is a unification between those. That doesn't really matter for most scientists most of the time, because if you're a chemist thinking about how atoms stick together by electrical forces to make molecules, then the gravitational forces between those atoms is weaker than the electric forces by nearly 40 powers of 10, so you could ignore it. Conversely, if you're an astronomer and you're thinking about the orbits of planets around the sun or planets around other stars, then all the orbits are slightly sort of fuzzy because of quantum uncertainty, but that fuzziness is tiny and negligible because they're so big compared to atoms. And so astronomers think about gravity, whereas in the micro world, we have to think about quantum theory. But if we consider the universe and the picture which has emerged in the last 50 years, that it expanded from a hot, dense beginning, then if we go right back to the beginning, then we have to think about what happens when the whole universe gets so compressed that we have to worry about quantum effects, as it were, shaking the whole universe around. And to understand the really earliest phase of the universe, we may need this huge breakthrough, this big unification between the forces governing the micro world and Einstein's theory. It's not clear how quickly we'll achieve that. And also it's not clear how we'll test that theory. The test will probably also have to come from observations in astronomy, because obviously the very extreme conditions of the early universe or black holes can't be replicated in the lab. So anyway, I've gone on long enough, but I think that indicates that we've got to unify Einstein's theory now with the theories of the micro world, the electric, magnetic, and the nuclear forces.
Professor, when at that time when I met you in ISTP, I mean, in 2014, I mean, there are many questions. One of the questions was, I mean, we know that the next step is to merge Einstein's general theory of relativity, which is, I mean, work perfectly in the macroscopic world, and quantum mechanics, which work perfectly in microscopic world. The problem now, what's the strategy? Because I think there is no one up to now the best strategy to merge those two theories. One of the, I mean, people think that maybe the problem is with the general relativity. It's a classical field theory. We need to write this theory as quantum field theory, then we, I mean, search for the merging. This one school of thought, I mean, there is other school of thought, maybe there is a different, higher mathematical abstraction, an elegant theory, which is a generalization of these two things. And some of them, which is the last fashion, some of them like Sheen Carroll and other things, thinking that maybe we start by quantum mechanics as fundamental, like, for example, the concept of quantum entanglement, then maybe we can derive the classical world, which is general relativity, from this quantum things. So depending on your experience in the field, what do you think the right path? Do you think that we know first the right path? Secondly, what's your opinion about this all speculation right now, because there is no experimental fact?
Yes. Well, let me say at the start, I'm not a great expert on any of these particular ideas. String theory is very heavily studied and has been for the last 30 years. And there are other ideas like loop quantum gravity and other newer ideas. And I think it's great that people are thinking about these. But as you imply, it's going to be very hard to test them. For string theory, the problem is that the mathematics is very hard, because in most versions, you've got to think in terms of the geometry of 10 dimensions, and that's very hard. And also, the crucial effects happen under extreme conditions that we can't reproduce. So I'm rather pessimistic about how quickly we will ever be able to decide if string theory is correct. I mean, I think, incidentally, artificial intelligence may help. Because, you probably know that machines have been able to learn very quickly how to play games like chess and Go, as well as a world champion. They can do calculations a billion times faster. And so it could be the situation that there is a theory involving 10-dimensional geometry, which does explain not just gravity, but explains the microworld, explains the why there are electrons and neutrinos and things like that. But it may be that the mathematics to get to that conclusion is too difficult. It may only be done perhaps with a computer. And so the one thing which would make you sure that the theory was correct would be if you could put in some general equations and the computer churned away and eventually came out without being told with correct numbers for the mass of the electron, the strength of gravity, etc. If that's possible. But I'm not optimistic, but I think it could be that we will have to use machines to help with the calculations.
Okay, Professor. Also, Professor, now, I mean, maybe we go to your field of expert. I think when we discuss about particle physics or standard model, we know that the formalism, the mathematical formalism, is quantum field theory, which lead to this beauty. For for the cosmology, I think the framework of, or the formalism of general relativity lead to the cosmology. And as you know, I mean, the Big Bang theory, which is for up to now, it's, I mean, the best theory we have in cosmology. Maybe in the future, we don't know. Maybe some of the big name like Roger Penrose and also Stephen Hawking before he died, I mean, and many names, I mean, try to think about new idea and new, maybe we tell, as you said, new speculations. Maybe can you tell us about the Big Bang theory? What's the good things? What's the limitation? What's the problems? What's your opinion about these things?
Well, I mean, I was a student in the 1960s, and at that time, it wasn't clear at all whether there was any kind of Big Bang, because there was a rival theory called the steady state theory, according to which the universe was expanding, but always looked the same, because as galaxies moved apart, new ones formed in the gaps, as it were. So we didn't have any clear-cut theory, and there was no evidence at that time, because with telescopes, we couldn't then look far enough away to observe far enough back in the past to see possible changes. Whereas things changed in the 1960s, and the most spectacular change was the discovery of what's colloquially called the afterglow of creation. This is the microwave radiation filling the universe, which is radiation with a spectrum of a black body of just below 3 degrees Kelvin. And this thermal radiation is believed to be the relic of the universe's hot, dense beginnings. The idea is that at some early time, the entire universe was hot and dense, like the inside of a star, and it expanded and cooled, and that radiation fills the universe, got nowhere else to go, and it's now filling the universe in the microwave band. Now, this theory that the universe expanded from a hot, dense beginning, this has been calculated, and we can calculate, if we assume relativity, how fast it goes. I mean, how long it spends at 1,000 degrees, at 1,000,000 degrees, at 1,000,000,000 degrees, etc. And one of the first corroborations of the Big Bang came again in the late 1960s, when people calculated what would have happened at the time when the universe had a temperature of a few billion degrees. And that would be for the first few seconds of the universe's history. It would then be expanding and cooling at a time when nuclear reactions could take place. And several groups did calculations of what the nuclear composition would be of the material emerging from that. And they found that it would be mainly still protons, hydrogen, but there'd be about 23% of helium and traces of lithium, but there wouldn't be any heavier elements. And fortunately, astronomers were able to take spectra of galaxies and estimate the proportion of helium, and it was consistent with that. The helium, even in the oldest galaxies, was about 23%. So that's a strong corroboration. And the third corroboration that's come more recently, which is that if we look very carefully at this radiation and observe it over the sky, then it's not quite the same in temperature everywhere. It's as though the early universe is slightly irregular, with sort of ripples in it. Some regions slightly overdense, some slightly underdense. And what's been really marvelous is that if you do a computer simulation and you start off with a universe that's hot and dense and put in these fluctuations, then follow it forward and the effects of gas dynamics and gravity, you end up with structures rather like the galaxies we see, clustered the way we see. So we've got a fairly good reason for thinking we know what the universe was like in its fairly early history. And by its fairly early history, I mean actually all the way back to a second. Maybe that's when the helium was formed. And I would go a bit further and say we can probably take seriously our extrapolations back to the early universe, back to a nanosecond. That's the time when the average particle would have an energy of about 50 GeV, which is about the maximum energy we can produce in a Large Hadron Collider. But of course, it turns out that many of the important questions about the Big Bang, namely, why is it expanding the way it is? Why does it contain the observed mixture of radiation, nuclei, and some kind of dark matter? Those questions probably have answers that lie even earlier within the first nanosecond. And of course, on a log scale, there's lots of time there. And indeed, many people think that a crucial period was at about 10 to the minus 33 seconds, when the particles had energy of about 10 to 16 GeV. This is an energy which is important in some grand unified theories. This is when it's thought that the expansion of the universe went through a so-called inflationary phase, very fast, etc. Although we don't have a detailed theory for how material behaves under those conditions, we have this theory which does have some evidence for it. If you look at the fluctuations in the universe, they have the property you'd expect if it underwent this period of inflation. So this is a long way of saying that we have good evidence for the idea that the universe has expanded from this very, very early dense phase. But of course, right back at the beginning, we just don't know, because the physics is certainly not understood, and we'll certainly need a theory that combines gravity and quantum theory to go right back to the beginning. And incidentally, the characteristic time scale, which is 10 to the minus 43 seconds, and a certain length scale, 10 to the minus 33 centimeters. Those are called the Planck time and the Planck length. And they are they're very, very important. And those are the scales when we are pretty sure that we need a quantum theory of gravity. But the Big Bang theory is well tested, I would say. But of course, right at the beginning, we don't know the physics, and we could, maybe the extra dimensions manifest themselves over and above the three that we observe. And of course, there are some theories which say that there will be many Big Bangs and not just one. This is an idea of eternal inflation proposed about 30 years ago by Andrew Linde, the great Russian cosmologist. So lots of uncertainties, but I think the progress going from a stage when we knew nothing about the history of the universe to being able to talk with few percent precision about everything back to a fraction of a second is one of the great triumphs of science.
So thank you, Professor, for this point. So I would like to mention something. So after the Big Bang, I think there are a lot of puzzles, problems, facing this theory. Also, there is also some problems in theoretical physics in general. For example, like the past hypothesis, why, for example, the entropy is so low in the past and not in the future, why there is an arrow of time, why this asymmetry between matter and antimatter, and all these things lead cosmologists like maybe Neil Turok, Roger Penrose, Stephen Hawking, and maybe you and other names think that maybe there is no one Big Bang, maybe there is many Big Bangs, there is, as you said. And recently, I think the most important two fundamental questions in the modern cosmology is the first one, was it a one Big Bang or more Big Bangs? And the second question, in case of there are many Big Bangs, are the laws of physics the same, or maybe changes, or what's the situation there? So I hope to maybe enlighten these two fundamental questions, depending on your opinion, Professor.
Well, I think you're quite right, but just to emphasize that I think what I said about the history of the Big Bang, after the first tiny fraction of a second, would be agreed by all of them. I think that no one disagrees that the universe has expanded from this very hot dense phase. But what they don't know about is what happened in the first tiny fraction of a second, and also what may happen in the very far future. And also, as you say, are there many Big Bangs, not one? Linde has a theory that naturally predicts many Big Bangs, and that depends on particular assumptions about the physics at 10 to 16 GeV when inflation occurs. You make some assumptions, you get what he calls eternal inflation, other assumptions you don't. If you get many Big Bangs, then as you say, there is the question of would they have the same microphysics as ours or not? And this is something which the string theorists address, because in many versions of string theory, there are many possible vacua, situations of empty space. And in those different vacua, then the laws of microphysics would be different. And of course, we just don't know. We can speculate, and it's quite amusing to think about counterfactual universes where gravity is stronger or weaker, or where the nuclear force doesn't exist, etc. But we've no idea if there's any basis for that in reality. And these are all these big questions which we can't yet solve until the big breakthroughs in physics. But this is true of all of science. As science advances, the frontiers get longer. If I think of the questions that were being asked when I started in cosmology, they've all been settled. We're now addressing questions like the ones you've just posed, which couldn't even have been posed back 40 years ago. So there's progress, but each advance brings into focus a new set of more fundamental questions. And can I make another point? I said that AI can perhaps help, but I think we've got to be open-minded about something which is that there may be some deep laws of nature which our brains just aren't capable of understanding. Because I mean, a monkey can't understand quantum theory, and there may in the same way be some fundamental features which would be essential in answering some of those very basic questions which you've just stated. And it may be forever beyond our grasp. I mean, it may be that we can use AI to actually do calculations we couldn't do ourselves, but we will never perhaps have the sort of insight that you have if you've made a discovery and had a new insight, like Newton or Einstein had, because it may just be too difficult for our brains.
Professor, right now, as you said, maybe we can say that all this maybe proposals are maybe speculations up to now. Yes. So we have a lot of speculation on table. I mean, maybe to replace or to generalize this idea of Big Bang Theory. So maybe as you are aware of about the work of Roger Penrose on something called conformal cyclic cosmology. Yes. And the other things, I mean, there are other models like the CPT cosmology with Neil Turok and his collaboration, and are many models. So now, when, as you are cosmologist and astrophysicist, we have a table, we have speculations, many speculations. What is the judgment, or what is the best way to select the best scenario among them? Is it the cosmological observation, experimental facts, or maybe there are some other things, lead to the selection of the best scenario after the Big Bang?
Yes, well, of course, that is the important question, because one has to explain a lot of data, and I think one possibility is that we will have a theory which does integrate gravity with the micro world, and if it does, then that will give us a set of physical laws which can be applied to the very early universe, and it may then tell us did inflation, etc. So that may happen, and this also may tell us whether what Roger Penrose suggests about his rather imaginative kind of cyclic universe would do. But I think at the moment we are far from testing them. There are some observations which will help, because, for instance, if you want to pin down what happened during the inflationary phase, then the amount of energy left behind in gravitational waves is an important new thing which we may discover from observations in the next decade, and there are other things like that. But it's going to be very, very, very difficult. And perhaps there's another thing which we haven't mentioned, which perhaps I want to bring in, and that's about the far future. One of the big surprises which came 20 years ago was that the universe is not just expanding, but accelerating in its expansion. And this was a big surprise, because people expected that the universe would be slightly decelerating in its expansion, because every galaxy exerts a pull on every other galaxy, and that's slightly decreases their relative speed, whereas it's speeding up. And so that means there's a new force latent in empty space, which is able, given how diffuse the density is in most of space, is able to overwhelm gravity and give a push which overwhelms the pull from the mutual attraction of galaxies. And this, which is actually a modern version of Einstein's cosmological constant, is a fundamental problem of empty space. And we don't know why this force exists. And I think to explain that force will be as difficult as to explain the Big Bang. And the reason is this, that if empty space we think of as being sort of featureless, nothingness, but if we believe in the quantum principle, then there's a limit to how much you can chop up empty space. We know that you can't chop up a table indefinitely. You can get down to the scale of the molecules or the atoms, but then it becomes granular. Most people, certainly those who believe in string theory, suspect that the same is true of empty space, that you can't subdivide it indefinitely, and that there's a totally scale. This is a scale I mentioned called the Planck scale, and a way to think of that is that it's a scale when a black hole has a radius which is equal to its Compton wavelength. So it's the smallest size of black hole you could make, because if you make a black hole which is small, then the smaller it is, the more you have to worry about quantum uncertainty. And this characteristic mass, which is a black hole of 10 to minus 5 grams and a radius of 10 to minus 33 centimeters, this is one whose Compton wavelength is the same as its Schwarzschild radius. And I think most theorists, and I think not just string theorists, suspect that on that time scale, and on a spatial scale, then you have to consider space and time as being granular. And in string theory, of course, that what you would predict is that what we think of as a point in our three-dimensional space is actually a wrapped up origami in maybe 5 extra dimensions. And those extra dimensions didn't expand with the rest of the universe. That's one idea. And so the effect of empty space not being completely featureless and having a force, a sort of tension in it that makes cause an expansion, that's something which again I think is going to be very, very hard to explain. So I think there are these big challenges, but I'm not optimistic in them being solved very quickly.
Me too, I think, and the audience with us. So I think you mentioned a very important point with, I think, the discovery of Adam Rees, who won Nobel Prize, about the cosmic acceleration, that there is an acceleration of the universe. It's not just an expansion, but also there is an acceleration. And this is lead to what called dark energy and these mysterious things and many other, speculations also about this dark energy. My questions, which is, I think this is the recent problem and the crisis right now. Now we are not discussing just about the cosmic acceleration, but also we have a different measurement about, measuring this cosmic acceleration. And I think you are aware about this, what they called it a new cosmological crisis, that we have 2 research group, the group of Adam Rees, and I think this work, with some methods, which is maybe the CMB and the other things, and we have the other group which work on the cosmic candles and the measurement. And we have, they are measuring the Hubble constants, and they found a big gap between the experimental measurement. Do you think that this is maybe just an observational or maybe data problems, or maybe there is some fundamental hidden theoretical things about the cosmological constant? Maybe it's not a constant anymore. Maybe the dark energy is, changing over time, or maybe there is some other fundamental clues. So I need, maybe it's better to hear from you, Professor.
Yes. Well, first, there are many theories which suggest that the dark energy may change with time.
Yes.
But even that doesn't readily explain the claimed differences in the Hubble constant.
By the way, this is, do you mean quintessence, the previous theory of quintessence, or other thing?
Well, there's a time dependent.
Dependent dark energy. Yes.
So there's a time dependence. I think it's always great if one can find some fundamentally new surprise, which would be indicated if the Hubble constant did behave in this rather complicated way. If you ask me to bet, however, my bet would be that the errors, particularly in the optical astronomy, are larger than they claim. And my bet is that the result will converge to something which is probably closer to the CMB value than to the earlier claims of the other groups, because they are getting different answers anyway from different possible stands of the candle. So my betting is that that'll be resolved in a rather dull way. But I hope I'm wrong, because it would be great if there was something new and exciting.
Maybe, Professor, just to give an audience, time for answering their questions. I have three more short questions, are fundamental about our thought. As a cosmologist, to tackle the next challenges or the actual challenges. The first question is, I invited Gerard Tooft, and as you know, is one of the great physicists, and he said that maybe the actual problems and why we are not successful to solve these big puzzles and problems, maybe we are not asking the right questions. The problem is the asking the right questions is not. So are you agree with this school of thought of Gerard Tooft, or what do you think?
Yes, I think I think that's true. We have to be open-minded, and there may be something fundamental new, because I think, quite apart from thinking of gravity, many people would say we haven't really got a full understanding of quantum theory itself. We know it's mysterious, and even if you just think of quantum theory, it may be that we need some new insight in order to make it seem less unnatural than it does now, and that's even more true if you bring in the others. So I think he's clearly right.
So the next short question also is, as you know, maybe most of these puzzles also is related to the finding a non-perturbative quantum theory of gravity, but falsifiable theory, as you know. So do you think that the problem, because now we have two big theories, one which is string theory and quantum gravity. Both of them work about the fundamental structure of space-time. So string theorists work about understanding the fundamental structure of space-time through dualities, through more symmetries, through these things. But the other part, which is loop quantum gravity community, try to maybe discretize space-time, try to understand the atoms, as we say, of the space-time itself. Do you think that this is, in general, the right path to find the quantum gravity is through understanding the fundamental structure of space-time? Or maybe there is another way, is to change the structure of the space-time itself, So what do you think about these things?
Well, I've got no opinion. I think it's good that there are two different theories, like string theory and loop quantum gravity being discuss
15
seriously.
hours.
But there are also new ideas. So just to repeat what I said earlier, I think these are deep mysteries, and we do need some new insights. But the problem is going to be to actually test any of them, because they're to see if they actually can explain things that we can observe or measure. But that the best we can do is to explore all the options, and indeed, as you say, hope for some really new deep insight, which may make us look at quantum theory in a new way, and may then suggest a natural way in which we can incorporate gravity.
Last question in my part, Professor, before I open the floor to the audience for their questions, is I think you know Lee Smolin is a faculty member of Perimeter Institute. I mean, sometimes one of his lecture called Time Reborn, he said one thing which is very important. He said maybe the problem is our method, I mean, to do cosmology. As we select, for example, we try to take a small part of the universe and try to find the laws of physics of this small part of the universe. Then after that, I mean, extend it to the whole universe. And even this small part of the universe, we try to neglect or to approximate things and to try to simplify things. I think he said that this way of doing cosmology and try to find fundamental laws of nature, maybe this is the main fundamental problem ever. So do you think, are you agree with this thought, or maybe you have other things?
I think, well, not entirely. I mean, of course, we couldn't do any physics and astronomy if the laws were completely anarchic, different from place to place. But we do know that in the entire observable universe, the laws of microphysics are the same and have been the same since the first second. Otherwise, we wouldn't get agreement with the calculated primordial helium, and otherwise the spectra of very distant quasars would look different in ways. So we know that in the domain we can observe, the laws of microphysics are the same. Now, going back to what you said earlier, of course, the observable universe may still be a tiny fragment of reality. It certainly is in the multiverse picture. And of course, as again you said, in those other universes, in the aftermath of other big bangs, the laws may indeed be different vacuum states, and string theory predicts that. But I think the laws of nature are pretty universal in the sense that they apply to the entire universe we can observe. But they're not universal, and they apply to the entire physical reality, which could be even vaster than what we observe.
So thank you so much for me, Professor. I have done, I mean, my part. I think it's better to open the floor for the audience. Please, for the audience, just I will speak in Arabic for the. So, السلام عليكم. الآن ندخل إلى الجزء الثاني من يعني الحوار بتاعنا أو اللقاء مع الأستاذ العظيم مارتن ريس. من فضلكم من يريد أن يطرح السؤال فليرفع يده، يعني just raise hand، يعني يرفع يده وسنعطي لكل المستمعين. So if the question, Professor, is in Arabic, I would try to translate it and translate it back. If in English, I mean, there is no problem. إذا كان السؤال باللغة العربية سيترجم، إذا كان يعني باللغة الإنجليزية سيمر الأستاذ دايركتلي. فمن فضلكم ارفعوا الأيدي وسنعطي أولا الأولوية للأساتذة ويعني طلبة، ثم نروح إلى فمن فضلكم ارفعوا الأيدي، يعني موش بالطريقة يعني العشوائية. So نبدأ. So محمد وهيب.
السلام عليكم.
وعليكم السلام ورحمة الله تعالى وبركاته.
مرحبا دكتور، أتشرف بهذا اللقاء وياك ويا الأستاذ العظيم.
ربنا يخليك.
الله يخليكم. أنا محمد من بغداد طبعا، نزياوي همين.
ما شاء الله.
الله يسلمك دكتورنا الغالي. على الوالي وأنت تترجم السؤال لأنه راح تنقل أفضل من عندي.
طبعا.
بالنسبة للموضوع بوزون هيجز والطاقة المظلمة والمادة المظلمة. إذا اعتبرنا بداية الكون يعني قبل الانفجار العظيم، كانت المادة المظلمة زائدا المادة العادية، يعني المادة والمادة المظلمة اثنيناتهن هن والطاقة المظلمة وبوزون هيجز موجودات بمكان واحد. لهنا أوكي دكتور تسمعني؟
ولكن أنت قاعد تقصد قبل البيج بانج؟
نعم يس، قبل البيج بانج، قبل الانفجار العظيم، لأن ما كان هذه كلها موجودات، هنا أصبحت موجودات بعد الانفجار. بدأت الطاقة المظلمة وتوسع الكون، ووجدت المادة المظلمة ووجدت المادة، وجد بوزون هيجز اللي هو أعطى للمادة جاذبيتها، فلازم هو موجود مباشرة بعد بداية الكون.
فالسؤال بالضبط ما هو؟
السؤال هل بالإمكان أن نعتبر أنه هي هذا تفسير لوجود المادة المظلمة والطاقة المظلمة أنه بعد الانفجار، وكان قبل الانفجار العفو كانت المادة زائدا المادة المظلمة كأنما نسيج واحد، مثل الملابس يعني، واللي مثل القماش والخيط اللي أو الثوب، والخيط اللي يلزمهن معا هو بوزون هيجز. فلما لسبب ما فتق يعني أو انفصلت هاي المادتين، أو بهاي اللحظة ظهر بوزون هيجز وظهرت الطاقة المظلمة اللي هي نتيجة هذا الانفجار العظيم. فإذا أنا أريد من جديد يعني أحصل على الطاقة المادة المظلمة، أريد أرصدها بواسطة الأجهزة اللي هسه هي موجودة وكلها مصنوعة من المادة، فلازم أرجع إلى الأصل، أستخدم بوزون هيجز بهاي الحالة. يلا أقدر أرصد يعني في هاي الحالة يلا أقدر أرصد المادة المظلمة مثل ما كانت بالبداية موجودة، لأن كل أجهزتي هي عبارة عن مادة.
ولكن سامح لي أخي الكريم فقط علشان نكون واضحين، أنت هذا افتراض أنه في مادة ومادة مضادة وفي طاقة
نعم افتراض، وأريد أشوف رأي الدكتور ورأي حضرتك في هذا الموضوع.
أوكي ما في لا أنا حكلم يعني حنقله للأستاذ دايركتلي هو اللي يجاوب. بروفيسور مارتن. Professor Martin?
Hello.
Yes. So Mohammed Wahib is from Baghdad, so from Iraq, and he Baghdad from Iraq. He asked the questions about, I mean, he suggests or maybe he proposed if there is maybe a dark matter and matter, and also the Higgs bosons or Higgs field before the Big Bang, and all merged together. Is it this proposal? Do you think maybe it's a solution maybe of what happened after the Big Bang? I don't know. I didn't understand very well the questions, but I said to him, for the scenario before the Big Bang, there is no obvious scenario. All things are speculation. But I want to hear from you. I mean, you can answer him directly, please.
Yes. Well, I mean, I think those are all mysteries, and we want to understand, was there really a beginning? Did space and time completely change? And are there many Big Bangs? We just don't know. We must hope there is some understanding. Of course, some people ask, could there be an infinite past? Whereas others say, like Stephen Hawking, that asking what happened before the Big Bang is like asking what happens if you go north from the North Pole, and you just can't do it, it'll close up on itself. But the simple answer I can give is that we just don't know. These are mysteries which will challenge theorists for the 21st century and maybe beyond that.
Thank you so much, Professor. I mean, we have here three professors, which I know them. If they have a question, please open the mics and ask directly. So Professor Basil Tai or Dallal or Saeed Sabbagh, if you have any question, please open the mic, and you are very welcome to give your. We have also Professor Tahsin Mubarak, I mean, from Jamiat Diyala. So those four professors, if you have anything to say, even to say hello to the professor, I mean, I am happy to, to hear from you before going to the audience.
You are most welcome,
Professor Basil.
Professor.
Okay.
Okay,
so,
Dr. Basil, it's okay.
Okay. So go on, Professor Saeed Sabbagh.
Yeah.
With us, Basil. So, as you, maybe we can start with Professor Basil. Yes. Okay.
Good evening, Professor Martin Rees.
Hello.
Since I was a student at Manchester University about 43 years ago, you were an icon for me. You know, I did my PhD under John Stewart Dowker, and I was really pleased to read your papers at that time. Dowker, as you know, was at that time in quantum field theory and curved space-time. And this approach, in curved space-time, gave us the chance to merge quantum mechanics on the right-hand side of Einstein field equation and classical general relativity on the left-hand side. And we achieved something. I mean, we published some interesting papers at that time. Recently, I mean, not quite recently, about 10 years ago, I revived my ideas and tried to build up a model which starts with the vacuum energy, vacuum expectation value of the energy momentum tensor of some quantum fields, and get that to build a model for the universe. We did achieve such a model, and my work was published in the International Journal of Theoretical Physics. And the model is, strange enough, is free from all the Big Bang problems, free from the 3 or 4 major problems, like the problem of horizon, and the problem of the magnetic monopole, the problem. We could explain everything, but it contained a very, very small amount of continuous creation of matter. Even less than the steady state model. Yes. Less than, because our rate of creation of matter goes like proportional to the radius of the universe, not to the radius cube. That's why our model suggests, first of all, it suggests that the universe is at all time maintaining the critical density, and at the same time, the critical density is time dependent. Obviously, in our model, as you mentioned in your talk, we use the time dependent cosmological constant. And it gives us a very good results. As far as the CMB is concerned, we do have a microwave cosmic background in this model. But I'm not sure why the physicists are not taking such models seriously. I mean, why do we have to stick to the standard Big Bang model, whereas there are other models which could provide, let us say, better picture? Yes, yes. This is my question.
Yes. Yeah. In fact, I don't know this model, but I'd just like to say that, in fact, the simple model does work amazingly well.
Yes.
There's no obvious contradiction with it. It raises its fundamental problem, but in terms of the simple model, it does explain the details of the age of the universe, the acceleration as a function of redshift, and also, more importantly, the formation of galaxies and how big they are and how they're clustered, and relates that to the fluctuations in the microwave background. And so, for instance, one thing which which may not be true in others is that in order to get galaxies now, the amplitude of the fluctuations you need in the universe may be different from what is observed by the Planck spacecraft, etc. What's so nice is that within 10% precision, the amplitude of fluctuation is just right to give the degree of structure we observe now. That's just one thing. And so people have been gratified by how well this simple model works. But of course, it still leaves unexplained why the dark energy exists, why it has the value it does, and also all the other questions. But
well, the dark energy in our model is the same as the cosmological constant, or the so-called cosmological constant, although it is time dependent, by the way. It has to be a time dependent. Also, we get we get right results for the other questions which you mentioned. Same results. I feel it is the dogma which we, the theoretical physicists, have brought up with, that is not allowing us to think beyond the box, as they say.
Just one point. I think you'd have to check whether you can get the galaxies, because if you have a higher energy density in the vacuum early on, then it speeds up the expansion, and you don't get the factor of 1,000 growth between the recombination era and the present.
No, we get that exactly, because we are at the critical density all the times. I think this is a measure
but a density in the unclustered component does not contribute, and so if the unclustered component dominates, then
you are right.
So we can't do this more, but that's a thing you need to check.
We have to look at this again. Yes, the young cluster. It's a good point. Thank you, Professor Rees. We are delighted really to have you this evening. I am very pleased to have you. This is the second or the third time I see you. Once I saw you in Doha. There were a conference in Doha. Right. And I asked you a question, if you remember.
It was a very nice conference.
That's right. Yeah, indeed. Thank you so much, Professor.
We can take another. Thank you so much, Professor, by the way. Thank you so much. So we can go to Hanna Sabat. If you have any comment, Professor, or anything, go ahead. Hanna Sabat.
Good evening, sir.
Hello.
Good evening, sir, Martin. Can you hear me?
I can hear you, yes.
Oh, I'm very sorry. Thank you very much for this interesting talk. Though I lost part of it, unfortunately. So I had this question about the Hubble tension.
Yes.
So can you just very briefly tell me how can it be solved, please?
Well, I mean, it may be fundamental, but if you ask me to bet, I think that they will find that the uncertainties in the astronomical measurements of supernovae and giant branch extreme things, etc., are larger than are predicted. So my betting is that the tension will go away and that it will converge on a value close to the one given by the microwave background. That's my betting. I hope I'm wrong, because it would be great if there was something fundamentally new. But my betting is that they're already finding more uncertainties in the calibration of the horizontal branch stars and the supernovae, and I suspect that that's a bigger uncertainty than they think. But that's just my bias. But I would take a bet on that. But I hope I'm wrong.
Okay.
If you'd like something more exciting. Yeah.
Okay, thank you very much. Thank you.
So thank you so much also for Professor Hanna Sabat. Thank you so much. So Dr. Sabagh, also, I think if you are here, you can give Dr. Sabagh.
Yes. Just again, nice to see you.
Hello.
And I want to know your opinion about two things, about chaos theory. And is it really could be a solution, or we don't know what is the correct solution?
Chaos theory. Well, I mean, it's certainly very important in trying to understand what happens in the later nonlinear stages of galaxy formation, but it only operates if you have a time available which is longer than the characteristic time over which things are changing. And I think the early, almost homogeneous stage of the universe would not be an arena where you would expect that theory. It comes in later.
And also about the time of the universe. In my life, you change it from 8 billion to 13 billion.
That's right, and I think it's now the value they quote is 13.8 billion, and I think the uncertainty which is claimed in that number is only 1 or 2%, and it is really marvelous that we do have a consistent model which pins down these important numbers: the age of the universe, the density of baryons and of dark matter and of dark energy with this degree of precision. So there's something right about the present theory, even though it confronts us with these problems of the very beginning.
Thank you very much.
Thank you so much, Professor Saeed Sabagh. Thank you so much. So if you have also Professor Shawqi Dalal, do you have a question? Or maybe we can go to Professor Tahsin from University of Diyala. Maybe just you can tell a few words or welcome the professor. Professor Tahsin Mubarak. So maybe we can go to the audience and we return back. So Rafiq Aoun, Dr. Rafiq Aoun, open the mic, please.
Yes, good evening, sir. Sir, how are you doing? Hope you are doing fine. I have a question about unification of quantum field theories and the gravity. You have said this can be a key to understanding among, for example, the creation of the universe, or starting from a universe as being a point to black holes. Are there any other cosmological phenomena which can be explained unless we unify gravity with quantum mechanics? Or
No, I mean, I think we will need a theory like that to understand the beginning of the universe and to understand the dark energy, I think. But we don't yet have that, and discussed earlier the very option. They're a long way, I think, from having a theory that we can test.
Okay.
Dr. Rafiq. Dr. Rafiq. So maybe we go to the Rafiq.
Yes, do you hear me?
Rafiq.
I hear you, Mohammed. I hear you.
Yes, yes. I think you had some few problems, but now you can go ahead again.
I'm done with the question. Thank you so much, Mr. C. I have some connection.
Ask your question, please, Rafiq.
Yes, I'm done with the questions. I'm having some problem with my connection at home. I'm sorry.
No problem. So maybe we come back to you when the problem is fixed. Professor Shawqi Dalal, open the mic and you can ask your question.
Yeah, the mic is open. Yeah, I have just a question about the formation of galaxies. In fact, if we look back in time, we find galaxies with supermassive black holes just 200 million years away from the Big Bang.
Mhm.
So this is very short time for producing such a massive supermassive black holes. So the question is, are these supermassive black holes formed before before the recombination era? That means all these supermassive black holes are primordial, I call them, as suggested by Hawking.
Yes.
So in fact, whenever you look back in time, always there are supermassive black holes at the center of galaxies, and these supermassive black holes cannot be formed simply in a short time by accretion or by collision of other black holes. Otherwise, we should observe the gravitational waves coming from these collisions of black holes to form a supermassive black hole.
Yes.
So the idea is all these massive supermassive black holes are formed in primordially. That means before the recombination era. So any comment about that?
Yes. Well, of course, there is the idea about small primordial black holes, but just 2 points. I think it is possible to understand how the black holes form at the same time as the galaxy. The material that is in the central part of the galaxy goes into the black hole and collapses, and the mass of the black hole is never more than a few % of the mass of the galaxy. So if the accretion can be very fast, then I think that would work. And I don't think we yet have any limits from gravitational radiation, because it's true, as you say, that gravitational waves are produced when there's a merger, but those are low frequency gravitational waves, which can't be detected by LIGO, but will be detected by an experiment called LISA, which is a space interferometer.
Yeah. Yes.
So we have no constraints on that from gravitational waves yet, but they have to go very fast. And this is one of the things I've written papers about, and it's surprising, but I don't think there's any fundamental mystery.
Do you think that Webb telescope will solve this problem?
Sorry?
James Webb. Do you think that James Webb telescope will solve this problem?
It will help, because it will observe galaxies at redshifts of more than 10, and so it should be able to solve it far better, because we have a few galaxies redshift of 10, but they're only ones which are detected because they're behind a cluster of galaxies which act as a gravitational lens. So they're a small sample, but the James Webb telescope ought to help a lot, yes.
Thank you.
Thank you, Professor.
I have just another question, but I don't know.
No, there is no problem, Professor Shawqi. You go ahead.
Yeah. In fact, you are talking about space-time as consisting of something. Now, there is a new theory coming up, which is called subquantum gravity. Now, subquantum gravity suggests that space-time itself consists of very, very small particles called etherions. Mm-hmm. We have about 10 to the 65 etheron per centimeter cube. That means if you take one proton or one electron, this will contain billions and billions and billions of etherons. Mm-hmm. Now, using this theory, the author, I think called the Paul Violet, he constructed many ideas regarding the fundamental physics, the Einstein theory of relativity can emerge from this. Also, the standard model can emerge from this theory, and many other cosmological observation also can be explained by this theory. Do you have any idea about such a thing?
I don't know this theory at all, but I think it is very good that people are exploring all these options. I'm sorry, I can't say any more than that about this.
No, because the big question, of course, is a question of quantum gravity. Quantum gravity, now, the forces are determined by exchange of bosons. Okay, so for gravitation, for example, you have exchange of graviton. For gluons, gluons are the messenger between quarks, etc. Now the question is how we reconcile this idea of exchange of bosons to produce to have a force, to have a gravitational force, with the idea of curvature of space-time. Curvature of space-time is completely a geometrical problem, whereas exchange of graviton, this is a kind of quite different idea. So can these two ideas be reconciled in one picture according to what we know now in physics, or we need a theory of a quantum gravity to explain this idea?
Again, I speak from ignorance, but I would guess we will need a theory of quantum gravity or a new way of thinking of space-time. Yep.
So thank you, Professor Shawqi Dallal. Thank you so much for your contribution. I hope that Professor Rees, answered really well, your questions. So we move to Nidal Salama.
مساء الخير دكتور محمد.
مساء الخير أستاذي، كيف حالك؟
أيها الصديق.
ربنا يخليك إن شاء الله.
Also, I am very nice to be with Professor Martin Rees this evening.
I think that your camera is reversed. يعني الكاميرا مقلوبة أستاذي.
I have a problem with
كذا كويس. This is much better. كذا كويس.
عندي سؤالين دكتور محمد. السؤال الأول about the gravitational lensing. Are we sure 100% that gravitational lensing is caused by dark matter? Also, the other question, we know that space-time is an approximation.
Yes.
Due that it has two singularities, as you know, and it is not valid at each point.
Right.
But we notice that many of theorems are depending about space-time. Does this weakness of space-time reflected on that theorems?
Well, there are two questions. First, gravitational lensing in a cluster of galaxies is thought to be largely due to the dark matter. And this is really just a classical effect, weak field gravity, which I would have understood. That's straightforward. As regards what you're saying, certainly on the small scale, we clearly do need quantum theory. But gravitational lensing, I think, can be understood just treating the dark matter as a continuum.
So, Dr. Nida, is it? Are you satisfied? So, do you have other question, or is it enough for?
The other question about space-time, Dr. Mohammed.
The space-time is
space-time fabric.
Yes, I really can't answer that one, I'm afraid.
So I think maybe the audience doesn't know that the specialty of Professor Martin Rees is cosmology, astrophysics. It's not really quantum gravity and this kind of thing. Maybe he knows something, but it's not his direct specialty.
But I don't think anyone knows the answer to those questions.
Thank you very much.
Yeah.
Thank you. So we go to Rafiq. Is your connection is well now, or Rafiq?
Hear me? Do you hear me?
Yes. Yes.
Actually, I had only one question, and I am done. So Professor Rees answered my question before. Thank you so much. So maybe we can move on to the audience now.
Okay. So did you? Okay. The next is Hussein Al-Khaldi. Hussein Al-Khaldi, open the mic, please.
Okay, welcome, Sir Martin Rees. I have two questions about Big Bang. What is the difference between Big Bang theory and cosmic evolution? The second question is, does the universe stop expanding, and why is it accelerating? Thank you, sir.
Yes. Well, I think cosmic evolution we know is happening because when we look at a very distant galaxy, we know it is different in its average properties from a nearby galaxy. So we can actually do better than a geologist. We can actually observe the past and check our theories of galaxy evolution by observations. And we've come to understand the process whereby the universe changes from being early on hot, dense, and almost uniform to now being structured. And we can understand how those structures develop. And this all starts with the Big Bang, and that's where the mystery lies. So we understand how the universe evolves, cosmic evolution, and we're trying to fill in the details. And we've had a lot of success in understanding why galaxies look the way they look and why they're clustered the way they are. Lots of data, huge samples, literally millions of galaxies, and the statistics worked out well. But as I say, it all goes back to the very beginning where we don't understand the starting point.
So thank you so much. Yes, thank you so much, Hussein. So we go to the Mohammed Darwish.
Okay, thank you so much. Thank you so much, Dr. Akram. Happy to be with you and Professor Martin. My name is Mohammed Darwish. I am a PhD in astrophysics researcher at the National Research Institute of Astronomy and Geophysics from Egypt. So actually, I have a couple questions. The first one is, how far we can say that we understand the role of the gravity in the universe? And here I would like to highlight the dark energy. And the other question is actually related to my study in the PhD about the massive star. I would like to hear your opinion about how massive a star is formed. Thank you so much.
Thank you.
Yes. Well, your first question, I don't know if you've seen these computer simulations showing a segment of an expanding universe where they put in the dark energy, the dark matter, and the atoms, and they see how the density contrast gradually grows and eventually galaxies extends out. And I think it is amazing that these simulations do agree with what we really observe. So we know we're on the right track, and so we can understand the formation of galaxies, taking account of the gas, dark matter, and the dark energy. And so that's one question. For massive stars, we don't understand exactly what the distribution of stellar masses is. We know there's an upper limit, as you know, to the mass of a stable star, But of course, one interesting question, which relates to what was asked earlier, is that if a very large mass accumulates in the center of a galaxy, then it never becomes a star. It just goes on contracting, trapping its radiation, and it goes straight into a massive black hole. And of course, intermediate mass stars may explode as supernovae. We don't know, but what we don't know is what determines the distribution of the masses of the stars that form.
Okay.
Okay,
Mohammed
thank you so much.
Thank you so much.
Thank you so much. I just a little bit question is
Yes.
I mentioned here the dark matter. So I guess if we need to extend the electromagnetic spectrum to see the dark matter, do you have an idea about this this idea? So we can extend the electromagnetic spectra to see what we can't see. Like I mean, in the visible band, we can see the radio, and also we can say that those are the dark regions. So this is all the idea. So are you agree with me in this point, or?
Well, I mean, I think it could be that there are some gamma rays, because dark matter particles might collide and emit gamma rays. So it's possible that there will be detectability of dark matter because of the occasional gamma rays. But on the other hand, that's not necessary. It could be that it doesn't emit any kind of electromagnetic radiation. That's certainly a possibility. But one thing to link the two answers I've given, in the simulations of galaxy formation, they treat the dark matter as a set of uncharged particles that don't collide very much. They swarm that go through each other, and that fits. Whereas if you treat it as a gas, it doesn't work, because the gas, when it collapses, gives shock waves, etc. So we already have good evidence that the dark matter behaves like a swarm of particles which don't collide significantly with each other.
So thank you so much again,
Thank you
Professor,
so
and
much.
thank you for, yes, Mohammed. So now we go to the maybe we add just two more questions, and we go to the conclusion. Hira Polet is a Turkish student. Hira.
Hi, Mr. Martin.
Teşekkür ederim. Teşekkür ederim.
Yes. I have a question to you. I'm from Bilkent High School. Charge parity symmetry is the assumption that the laws of physics remain the same if a particle is exchanged for its antiparticle. This theory, which is used to explain the dominions of matter in the universe compared to antimatter, has still not been proved. If this rule can be violated, what about the laws of physics?
Yes. So I'm not quite sure I understand the question. You're talking about opposite charges and whether they're equal?
Yes, for example, symmetry is the assumption that the laws of physics remain the same if a particle is exchanged for its antiparticle.
Ah, okay. Yes. Okay. Yes. Well, of course, we know that that doesn't apply for the weak interactions, and it's certainly believed that there's some asymmetry which is true in the nuclear reactions, and that's the only reason that there is any matter in the universe at all, because when the universe was very, very hot, then there were particles and antiparticles as common as photons, and as it cooled down, then the particles and antiparticles combined, but they didn't all annihilate, because there was by that stage an excess of particles over antiparticles, and so the last ones couldn't find, as it were, a mate to annihilate with, and that seems to have happened, and that requires an asymmetry not just in the weak interactions, but probably in the strong interactions. But there again, the details are not well understood.
Thank you.
Thank you.
Hira, do you have another question or?
No, thank you.
Thank you so much. Thank you. So for, I think, maybe Mohammed Abdullah Mohammed.
Hello.
Hello.
Dr. Mohammed, I need to ask Dr. Martin about the anthropic principle, which we see. First, thank you for his book, Just Six Numbers.
Yes.
And if he has any book in future in anthropic principle.
Yes.
Thank you.
Right. Yes. I don't have a new book, but just to explain, this is the idea that perhaps there were many universes, and that's earlier questions, but they're governed by different physical laws. And it's very interesting to explore what they would be like. This was called Counterfactual Studies, and just like historians sometimes discuss, what would happen if the history of the world had been different. If certain wars had been fought, if America had been discovered much earlier or much later, etc. And we can ask what would happen if gravity was stronger, or if the nuclear force didn't exist. If gravity was stronger, then stars would be smaller and we'd be crushed by gravity, etc. And if there's no nuclear force, there'd be no periodic table. So we can say that the physical constants have to lie in a particular range in order to allow the kind of complexity and scale needed to have evolution like ours. And you can actually do these calculations just as a counterfactual story. But if some of these things in the multiverse are correct, then of course it may be that there are a lot of universes where the laws don't permit complexity to emerge. So they'd be sterile universes, and we will one of the privileged ones where the laws of nature do allow a periodic table and have a force of gravity which is non-zero but weak. So this is what's meant by anthropic selection. I don't think it should be called a principle really, but it's just the idea that the fact that we observe something implies a sort of selection effect, that we can only observe the kind of universes in which we could exist, whereas we can imagine lots of universes which we couldn't exist in. But those universes might be out there, but we just never observe them.
So, yes, thank you so much.
Yeah.
Professor, I think we, reach the final, conclusion, because,
yes.
Most of we have 45 interviews as I discussed, and we give the audience the same 45 minutes. So at the end, I will say, for me, before I will go to Professor Ibrahim Tijani from Dubai, he will, discuss about final things. He want to inform you about a new project. It's the same in British. So for me, thank you so much for accepting my invitation. I hope to see you in the future at Perimeter Institute or at any other place. And I am very happy to see you again. Since ICTP 2014. Thank you so much. It was very honor for me, to accept my my invitation. And if you have a last word to tell before going to Professor Ibrahim Tijani, he wants to mention a new things for you. Just a small. So that it's.
Well, can I thank you for the invitation, and just say I hope to welcome you, and indeed many of the other friends on this Zoom to come to Cambridge one day, come to England you get a very good reception, and so I hope we can see more of you in England, as the subject is so international. But of course, we also meet at places like Trieste and the Perimeter Institute, and that's also great. But let's hope we can meet in 3 dimensions, not just in 2 dimensions of these Zoom pictures. Thank you very much.
Thank you.
Thank you so much. Thank you so much, Professor. By the way, just before going to Professor Ibrahim Tijani, he will discuss about this new project. It's called Arab Royal Society of Science. We initiate this new, things. So Professor Ibrahim Tijani, it's up to you now. The mic is for you, Professor Ibrahim.
First of all, let me say thank you, Dr. Mohammed, for this new degree that you give it to me today, and my honor to carry this big name. And I think somehow I deserve, by this lovely evening, I deserve this, what you call me right now. So thank you, sir. And I have a lot of things to say about this, but actually, because I am not from the field, I'm not in this really amazing discussion that I hear for a long time. I never attend similar. Thank you for your time, for everyone, and thank you for the organized people. Thank you for the audience. Thank you for all the professor and doctor from the field. Thank you for the new generation that I saw it here. Like, I'm really proud about Dr. Mohammed Darwish and Professor Bilal and all the names that here they attend, and really they add value to this lovely evening. I don't know how to talk to dear Martin. Shall I call you sir or professor or doctor?
Just Martin. Just Martin.
Just at the end of the day, I respect your humanity and I call you Martin.
Yes.
I wish you accept that. So, Mr. Martin, we are really appreciate, and we are honorable to welcoming you here and to give us your time. And we know your time is so short and very expensive time that you give us to us. And we have something really very new, and by myself, I'm really proud to be part of it, to announce our Royal Society. As Dr. Mohammed just announced, it will be the first Royal Society, Arab Society in the region. And definitely we need your guidance, we need your expertise, we need your experience on that, and we need your kind support. And we wish to be part of this lovely globally institution like Canadian Royal Society, like Norway Royal Society, similar in UK. And thank you for inviting us to be part of your welcoming and the reception that you invite us to attend. Soon we want to see you in UK. And I don't have more to say than this. Thank you again. And I can just get this chance to also send the regard from Engineer Abdul Hafiz Ikhbariya, the founder of Hamsa Sama organization. He passed his regards to you. He had 2-3 things he got a chance to attend. So please, you may accept his regards. And the other organizer, Ms. Kifah Zakhalia, she is here. Also, she passed her regards to you. And definitely Dr. Fatima, the chairman of Hamsa Sama organization, I passed the mic to her. Maybe she want to add something before we close our lovely evening. Please, Dr. Fatima.
Thank you so much, Professor Ibrahim.
Good. Yes. Well, thank you very much indeed. And can I wish you the best of luck with the new Royal Society? There are federations of different academies which get together to be global bodies, and this will be an important new addition to the academies that already exist. So
thank you for these wishes, and we appreciate to be the good body and the good party of this association, globally body, to be part of it. And I hope to welcome you again in any part of Arab region.
Indeed, yes. Well, thank you very much, and thank you very much to everybody. I'll go on. My supper is getting cold,
Okay.
Oh, bon appétit.
Okay.
Bon appétit en advance.
I will go and have that now. Thank you very much.
Bon appétit.
Thank
Okay,
you.
thank you.
Thank you, Professor.
It's 9 in the evening here. Yeah.
Thank you. Thank
Yes,
you.
thank you.
Bye.
So,
شكرا لكم وشكرا لكل الحضور وشكرا لكل الغامات المتميزة بحضوركم الأنيق الجميل، وأنتم إضافة حيثما كنتم وإضافة حيثما حللتم. لكم التحية ولكم التقدير ولكم التجلة سادة العلماء، سادتي الأساتذة في مجالاتكم وتخصصاتكم المختلفة، والشكر عبركم للدكتور محمد أكرم فلاح، الرجل المتميز حضورا متميز في تواجده في كل المحافل العلمية وكل المدارس المتخصصة. فالرجل إضافة وهو كالغيث، حيثما هطل نفع وحيثما حل أزاد وأشرق. فلكم التحية كلكم من غير مسمى، مع الاحتفاظ بالألقاب، مع الاحتفاظ بمسمياتكم، مع الاحتفاظ بمقاماتكم السامية الرفيعة، وهي تجليات الله سبحانه وتعالى عليكم باسمه العليم، وبسط علومه لديكم فبسطتم لنا هذه العلوم وأسهلتوها علينا. فبارك الله فيكم وجزاكم الله عنا كل خير. وحقيقة يمكن أنا تحدثت في عجالة عن المجمع العربي للعلوم الذي سوف يكون إن شاء الله إضافة حقيقية لمعظم المجامع حول العالم، ولقد أطلقنا عليه اختصارا اسم معلم، وإن شاء الله في غضون هذه الأسابيع القادمة سوف يكون لنا بشرى بمشاركتكم لنا هذه الفرحة، وفرحة لا تضاهيها فرحة بأن نكون إضافة علمية كمركز متخصص يشرق ويبهر ويكون إضافة للمعالم حول العالم. وحقيقة فكرة وإضافة الفاوندر لهذه التظاهرة العلمية دكتور محمد أكرم فلاح، الشيء من أصله لا يستغرب دكتوري، فهذه إفرازة نشكرك عليها حقا. جبت بقاع الأرض من إفريقيا من جنوبها ومن شمالها حيث أنت هنالك، ومن كندا عبرها وإلى بريطانيا وإلى الجزائر مرة أخرى، وها أنت الآن في منطقة الخليج تزهر وتشرق مرة أخرى بهذا المجمع الذي أنت على رأسه في الإدارة الأكاديمية مسؤولا عنها بحثا وإشرافا وتنقيحا. فبارك الله فيك دكتوري وجزاك الله عنا كل خير في هذه الأمسية التي كنت غائد ركبانها علميا وفكرا وأدبا. زادك الله أدبا وزادك الله علما، ولك التحية ولك التجلة، والسلام عليكم ورحمة الله تعالى وبركاته. دكتورة فاطمة.
تفضل دكتورة فاطمة. شكرا جزيلا أستاذ إبراهيم على البلاغة الرائعة كالعادة والارتجال، يعني اللي ولا أحد شفت واحد ما شاء الله، يعني عندك لغة عربية رائعة جدا وبلاغة، وربنا يحفظك يا أستاذ. ويعني هذا يعني أيضا حتى المجمع هذا يعني أنت يعني جزء أساسي فيه، وأنت صاحب الفكرة، وأنت يعني أيضا شجعتنا على هذا، وربنا يخليك، وشكرا على دعمك الدائم أستاذي، ربنا يخليك انت والاستاذ. نروح الى الدكتوره فاطمه. يعني
دكتوره المايك عندك دكتوره.
يعني شكرا دكتور ابراهيم التيجاني اللي هو الامين العام لمنظمه همسه سماء الثقافي الدوليه، وشكرا للدكتور محمد اكرم فلاح اللي هو كمان من ضمن فريق همسه سماء الثقافي، الان اصبح من ضمن المجموعه. إن شاء الله كما قال لكم الدكتور إبراهيم في الأسابيع القادمة القليلة إن شاء الله سوف يعني نخرج عليكم ببشرى المجمع بإذن الله تعالى. شكرا لجميع من حضر معنا، شكرا كفاح، شكرا لكل الموجودين، شكرا لكل العلماء، شكرا للمهندس عبد الحفيظ غبارية المؤسس لهذا الصرح، يعني إن شاء الله سيكون صرح عظيم بإذن الله. وإن شاء الله دكتور محمد نلتقي معك بإذن الله في ضيف آخر من لقاء العمالقة بإذن الله تعالى. ونشكركم جميعا. شكرا كمان دور دكتور إبراهيم على حضورك وعلى كلماتك، وإن شاء الله مستمرون بإذن الله تعالى. شكرا لكم جميعا وتصبحون على خير.
وعليكم السلام ورحمة الله وبركاته.
وعليكم السلام ورحمة الله تعالى وبركاته.